Hi, Phil from statisticsmentor.com, and now we're looking at a third way of solving this lottery problem. Probability of winning the lottery given the 20 balls numbered 1 to 20, and we have to win. We win by matching 5. Here is quite a common answer I get from my students. I always get this answer coming out. So it goes like this. Right, first ball I draw, there's 5 numbers of them, and it's out of 20, so probability of drawing the first ball is 520. Second ball, now it's out of 19 because 1 is gone. Now there's only 4 balls of the matching ones left, so it's 4 over 19. And then likewise, I think you can see what's going on. Right, and this gives me the answer. Why do I feel uncomfortable when students give me this answer? Well, I feel uncomfortable because this thing about multiplying probabilities seems so to the students to be just something that you do. But there's a danger in this because it is not always the case that we can just multiply probabilities. And so I'm especially kind of comfortable when they do this, even though we haven't yet touched on Bayes' theorem, dealing with conditional probabilities. So let me explain. We can multiply probabilities of events. Say, let's consider 2 events. Say event A and B. A and B happening. Let's imagine like first ball is a winning ball, second ball is also a winning ball. You can multiply probabilities like this, like so, which we've done up here, only if the events A and B are independent of each other. So A and B, and we use this symbol, mutually independent. In other words, the outcome of one does not affect the outcome of the other. We can extend this rule to more, so if there are 4 balls, ball 1, 2, 3, 4, 5, then multiply the probabilities only if those events are mutually independent of each other. Hang on, since there are more than 2 events, let's drop the word mutually. They're independent of all the other outcomes. So is that the case here? We'll look at the second ball. What's the probability that this is what you've done here? Let's look at this expression is saying that probability of a win is probability the first ball is a winning ball, and the second ball is a winning ball, and the third ball is a winning ball, and the fourth ball is a winning ball, and the fifth ball is a winning ball, and you've multiplied probabilities. So you're assuming that the events are mutually are independent. Why do I keep saying independent? Okay. And now we'll look, for instance, at the second ball as a winning ball. What's the probability of the second ball being a winning ball? Doesn't it depend on whether the first ball was a winning ball? If the first ball wasn't a winning ball, then the probability of this being a winning ball would be 5 over 19 rather than 4 over 19. In other words, what I'm saying is that these separate events, they are not independent. So what do we do when the events are not independent? We apply Bayes' theorem. And the Bayes' theorem goes like this. It goes like this, that probability of A, if we consider 2 events, A given B, is equal to probability of A and B, joint probability, divided by the probability of B. Assuming here that probability of B is bigger than 0, because you can't go dividing a finite number by 0. Let AI denote the ith ball is a winning ball. And what we want is probability the first ball is a winning ball, the second ball is a winning ball, and the third ball is a winning ball, and the fourth ball is a winning ball, and the fifth ball is a winning ball. And we know that these events are not independent, so we have to apply Bayes, and I can show that it comes to this. And now we can write down the probabilities. What's the probability that the fifth ball is a winning ball given that all the preceding 4 balls were winning balls? Well, there's only 1 ball left in that case that is a winning ball, and this out of 16 balls, that's 1 over 16 times the same thing. What's the probability here that the 4th ball is a winning ball given the preceding balls 1, 2 and 3 were winning balls? Well, there's only 2 balls in there, and that's out of 17. Likewise for the other ones. Now, if you're a student and you wrote it this way around, then I kind of understand that you can see what you're doing. But most of the time students are writing the reverse way, like I showed you in the first case, which shows me they're not thinking about it like this. So that's why this actually coincidentally equals to the other one. So one way of seeing this is that the probabilities here, we're multiplying conditional probabilities together rather than the straight probabilities that we're using at the beginning of this session. One final thing is, well, I wonder, any of you interested in seeing the proof of this thing? Well, I think I'll do that in a separate video because I don't want to take away the importance of this point. Alright, so that is the way that you guys did it, but with a proper explanation here where I'm multiplying conditional probabilities.